All right, gang. In teaching Math 6610, it's really a struggle for me to figure out where to begin. Maybe as Yogi Berra would say, the best place to begin is in the beginning. Um, it's not that simple. The reason it's complicated is that students come to our program with such varied backgrounds in statistics. So I think I would not do the course justice if I skipped over this part. It's so tempting to just, you know, upload a data set and start crunching numbers and demonstrating different statistical tests that you guys will use in your research theses. Uh, but I think that again, I would do an injustice to you if I didn't cover these topics. Now, it's a struggle for me to not get on tangents. I'm going to do my best here. You might already say, Dr. Darbo, you're already on a tangent. But I find out if I get on tangents, then students don't stick with the videos and they don't watch them, which is just completely counterproductive. So let's get with it. So the purpose is just really some basic ideas and what we're actually doing in terms of, well, as you see on the screen, generating a research question, developing a theory to kind of explain the research question, breaking it down into something that's testable, collect your data, and then analyze your research question, analyze your data. So I've given you just, and I'm not going to read this to you, but on the left you have the the 5-stage process, and then on the right we have an example as example. There's a lot of emphasis today on remote learning. If it weren't for the option of remote learning, I don't think our program would be in existence today, that being the Masters of Mathematics, the program in which you are enrolled. Because we've been able to, by going fully remote, we've been able to reach out to a lot of students in various locations around the world, actually. So, it's reasonable to study this idea. Are online classes as effective as face-to-face classes? Now, the justification there is this generation, I think broadly defined, is very comfortable receiving information through technology. Then the next thing, on number 3, we would identify maybe a common set of questions to be used for online and face-to-face students. Examine exam scores, and then of course number 5, determine whether we need a t-test, ANOVA, and COVA, depending on a lot of different factors. So when we conduct statistical analysis, you'll see that we use this threshold of 0.05. So in other words, what we'll do is we will, and I'll give you more about this in this video, we'll create something called a p-value, which is a function of something we call a test statistic. And we'll compare our p-value to this alpha. And we typically set our alpha at 0.05. Now, why 0.05? What's so holy about 0.05? Well, I don't know. It's just the industry standard. And the industry standard for the confidence interval is 95%. Again, 5% plus 95% equal 100%. Imagine that. And there is a link there. There is a connection. I dove into the research to determine why we use 0.05, not 0.06, or why not 0.02, or why 0.10, whatever. And it seems to, the best that I can figure out, again, I spent far too many hours trying to figure this out, get a historical perspective again on why 0.05. And it seems to go back into the early days in banking, where most financial institutions were able to withstand a 5% error when lending money. So the error in this case would be lending the money to someone who could not repay the money. So we can see this kind of bounces off more broadly defined financial errors. So if we see the table here at the top, we say, should we lend the person the money? Well, we should or we shouldn't. And possible outcomes: the customer pays back the loan, they don't pay back the loan. Well, obviously, if we lend them the money and they pay back the loan, that was a good decision. Same thing if we don't lend them the money and they wouldn't have paid back the loan, also good decision. And the errors actually fall in the other two boxes. Now, it's a kind of a nice baseline to consider financial errors because it aligns pretty nicely with statistical errors. So when we create a test of hypothesis, we start out with stating a null hypothesis. Well, that null hypothesis that we're testing is either true or false. And the crazy thing about statistics, the thing that drives everyone nuts, drives everyone insane, including myself from time to time, is we never know if the null hypothesis is true or false. It's a statement about a larger population. We're making a decision on the null hypothesis based on information that we get from a sample, which is a much, much smaller collection than the entire population. So to the left, we have statistical decisions. We can either reject the null, in which case we have statistical significance, or we can fail to reject the null, in which case we do not have statistical significance. Well, obviously, if the null hypothesis is true, then we don't want to reject it. So the failed to reject the null decision would be the correct decision. Similarly speaking, if the null hypothesis is false, then we hope we reject. We don't want false statements hanging around. Let's say that someone says that the average ACT for entering students this year in all public universities and colleges in Ohio is 24. So let's say the mean ACT is 24. Well, if that's a false statement, we hope that we make a statistical decision that rejects that false statement, right? So that said, the thing that I want you to notice, or at least focus on most in this chart, is when the null hypothesis is true and we reject it. Well, that's called an error, and we call that a type 1 error. And when the null hypothesis is false and we fail to reject it, in other words, keeping false statements around, that's called a type 2. Now, if that's kind of bogging up the brain right now, let's go ahead and make it a little, put it in maybe simpler terms. So a type 1 error is rejecting a true null hypothesis. Type 2 error is failing to reject a false null hypothesis. Alpha, again, 0.05, the industry standard, is the probability of committing a type 1 error. So if we set our alpha at 0.05, which we typically do, now there are times we don't. There are times that we raise alpha and there are times we lower alpha. More about that on the next screen, or at least one of the upcoming screens. But back to the industry standard of alpha equal 0.05, we are allowing ourselves a probability of committing a type 1 error at 5% of the time. Beta, on the other hand, is the probability of committing a type 2 error. Beta is really, really helpful to us because it gives us a way to calculate what we call the power. So a power of our test is the probability of rejecting a false null hypothesis. Now, your head's probably swimming, especially if it's been a while since you've taken statistics, but these are just things that you have to tattoo to the brain, okay? Again, it's all coming full circle here about why do we use alpha 0.05? Well, it's just the industry standard for an acceptable probability of committing a type 1 error. What's a type 1 error? It's rejecting a true null hypothesis. Now, the next page here, the probability of committing a type 1 error, there are actually 4 common choices for alpha. I only listed 1, or I'm sorry, I only listed 3. I eliminated 1. 0.001, 0.01, 0.05, and actually 0.10 is actually another common choice for alpha. That would be a really good exam question because then I could focus in on students who are actually watching this video and sticking with me. All right, so who knows what will happen. Beta is a function of alpha. Let me explain. Well, here we go. The alpha of the four choices. I don't know why I deleted 0.10 from the previous screen. So if you look at, for example, an alpha of 0.01, that gives us a 1% chance of creating a type 1 error. Now you might say, well, why don't we just set alpha really, really low? In other words, at 0.001 of the ones listed. And you could even take this a step further and say, well, why don't we set alpha at 0.0000000, whatever one, put a bunch of zeros in there. Well, the reason is there is a trade-off. As we lower alpha, beta, which is the probability of a type 2 error, increases. So if we set alpha really low, then we increase the probability of creating a type 2 error. Contrary to that, if we set alpha high at 0.10, we're more likely to create a type 1 error, but we're less likely, and in fact I wrote it there, very, very rarely, would you create a type 2. So it may be kind of clear why 0.05 is kind of the balancing act between a relatively low probability of committing a type 1 error and balancing out a relatively low probability of committing a type 2. So I think that's really the reason that we land on, as the industry standard, alpha equal 0.05. Now, again, this is just kind of summarizing what I just said. So you might want to take a screenshot or put this, pause the video and put this in your notes. What's really important, well, it's all important, or I wouldn't have written it, but considering what I told you from the previous screen, I want you to bounce down to the last bullet. We have a desired level of power. And again, what's power? Power is the probability of rejecting a false null. It's the intent of any test. Whether you're doing a regression, ANOVA, ANCOVA, whatever family you're living in, whether you're predicting, explaining, whatever it may be, we will calculate a power. And we'll do a priori power, and we'll do a post power, but and I'll talk about that in another screen. But our desired level of power is 80%. Now, you run your power analysis and you find out that your power is 60. What do? Well, typically you increase your sample size or decrease variables. All right. So you can see the relationship there between a type 2 error, which is beta. So acceptable probability is 0.20 because power is 1 minus beta. And the focus is on trying to achieve an 80% power. Now, it's not that simple. If we get a 90% power, is that good? Well, yeah, we're going to have a 0.90 probability of rejecting a false null. But when we have a 90% power, then we get into the possibility of finding statistical significance when there's not practical significance. And we will run into that in future videos. So statistical significance, let's say, for example, well, what is statistical significance is when our p-value, the probability of attaining our sample data when the null hypothesis is true, or given the null hypothesis, is less than our alpha. So if we have a p-value that is less than our alpha, alpha is typically set at 0.05, then we have statistical significance. When you move into bigger level stats, you start dropping the phrases reject the null and fail to reject the null and start replacing that with statistical significance and not statistically significant. So again, reject the null is equivalent to statistical significance. Not rejecting the null is not statistically significant. So if we have a p-value, for example, of 0.032, our alpha would be, if our alpha was 0.05, which again it usually is, or for some reason we decided to set at 0.10, then we would have statistical significance because our p-value is less than both of those alphas. If our alpha was 0.01 or 0.001, then we would not have a statistically significant result because our p-value is higher than those two. And, can you say this without smiling? It is completely and totally unethical to set your alpha after calculating your p-value. So let's say you've got some prior intent, right? You want your test to, let's say you want your test to not be statistically significant because for some reason you think you have a better, higher hopes of getting your research published if you don't have statistical significance. And your p-value turns out to be 0.02. Well, you can't do something goofy and then just adjust your alpha so you don't have statistical significance. You set your alpha beforehand, again, usually 0.05, and then just compare your p-value. So if there's actually a book out there, How to Lie with Statistics, and that's actually one of them. All right, how do we calculate a p-value? Well, model variation, and that's what statistics is really all about. When people walk into a statistics class, they think averages and means and medians, measures of central tendencies. Actually, ladies and gentlemen, it's all about variation. And we think about our variation as explained and unexplained variation. We call it systematic variation and unsystematic variation. So we're constantly in our model diagnostics looking at what amount of variation does our model explain versus what amount of variation does our model not explain. Now this becomes a lot clearer once we dive into the ANOVA family. So I'm not going to spend a lot of time here. I just want you to have this in your toolbox, and I want you to know that this is important and it's going to be coming up in future videos. Now, what is super important, what I want to make much clearer and not leave you hanging, is a test statistic is just the ratio of the explained variation to the unexplained variation. And a test statistic is used to calculate our p-value. We'll learn many test statistics, z, t, f, chi-square. More about that later. So how do we report a p-value? Again, using the cutoffs 0.001, 0.01, 0.05, or possibly 0.10. Bouncing off the idea that 0.05 is the industry standard, again, which it is. If a p-value is higher than 0.05, then we just report it. If it's 0.82, then put p equal 0.82. If the p-value is less than 0.05 but higher than 0.01, then we report it as 0.05, p less than 0.05. If it's between 0.01 but higher than 0.001, then report as p less than 0.01. If it's less than 0.00, okay. If it's less than 0.001, then we report it as such. Report p-values to 2, 3, or 4 places. Just be consistent. So I'll give you some examples down there. If we have a p-value of 0.321, well, that's greater than 0.05, so report it. If we have a p-value of 0.032, well, that's less than 0.05, but not less than the next level of, right, 0.01, so we report a p less than 0.05. We have a p-value of 0.005. Notice it's less than 0.01, but not less than 0.001. So we report it at p less than 0.01. And the final example, less than 0.001. So, ladies and gentlemen, the test statistic is the ratio of our explained variation divided by the unexplained variation, or the effect over the error. And sometimes you see that as the treatment over the error. One thing to keep in mind, larger test statistics result in lower p-values. You're keeping everything else uh, consistent. So a test statistic using the t-distribution of 2.8 will have a smaller p-value than a test statistic using the t-distribution of 1.28. And if you have an F distribution, which we run into in ANOVA, 5.8 will have a smaller p-value than its lower F statistic of 2.0. Effect sizes. Effect sizes are complicated because they vary depending on the type of situation that we get. But what I want you to know for now is just because a test statistic is significant doesn't mean that it's practically significant. We can run into a situation where we have statistical significance, but not practical significance. So the effect, let's say, for example, that you and I, we as a team, develop a weekend ACT prep class. And we have shown, we want to show that students come in with an average ACT, and after taking our class, the average ACT increases. Well, let's say that we, through a lot of statistics and diagnostics and models, we show that the mean score coming in is a 24, and we increase it to a 24.01. Now, if you have a large enough sample size and a high enough power, you can find statistical significance between 24 and 24.01. You get a p-value less than 0.05, the world's happy, we can have breaking headline news, our weekend program works. Does it really? Is there really a practical significance, a practical improvement of an average ACT from 24 to 24.01? The answer to that is no. So we could end up with statistical significance, but not practical significance. Well, that's the motivation for effect size. Effect size are the standardized measurements that are somewhat and mostly independent of statistical significance and power. So they just hone in on, if you will, just a standardized difference, not necessarily, well, a standardized difference independent of the power analysis. I believe that's it. Now there's one more. Okay, I'll give you an example of an effect size. If we have an independent samples t-test, we use an effect size R. There's so many different effect sizes, omega squared and nu squared. I mean, there's so many, and that's what makes it so complicated. So what you have to do is you just, and I don't remember these things. I just tell you, and I do this stuff every day. What I have to do is I just have to have things organized. Also, I use Google. So if I'm running some, let's say I'm running a logistic regression. Well, that's a horrible example because effect size for a logistic regression is extremely complicated. But let's say I'm running a two-way ANOVA, and I want to know how to calculate and report the effect size. I'll just Google it, because I'll tell you right now, I don't remember how to do that. Even though I've done it many times, I don't remember that. There's just too many of them. So keep it real here. But if you're somebody stops you on the way home tonight and they says, okay, you're taking Darbo's stats class, what is the effect size calculation for a t-test? Well, there you go. You're in business. All right, gang. A couple of more things. The power of a test, again, is the probability that a test will detect a difference. And we aim at a power of 0.8. Well, that is almost it. Yeah, these screens keep popping up that I forgot about putting here. Achieved power versus priori power. This is extremely important. So let me explain that. A priori power is something that before you ever start collecting your data, this is really after you've created your research questions, You've embedded it in theory. You've determined the type of statistical technique that you're going to use. You would run a priority power to see what sample size you need to achieve a power threshold of 80%. And achieved power is kind of like a post hoc power. Once you've run your analysis and you have your test statistic and you have your p-value and your confidence interval, you can actually determine the power of the test that you just ran. So priority power helps you plan in terms of how many subjects you need to collect to be able to meet, again, the threshold of 0.8, and then the achieved power tells you what you actually did. And we use G-power for these calculations, and we will have some textbook examples throughout the upcoming videos. So what do you do if you set your priority power and you determine you need 250 subjects, and you get 250 subjects, and you run your analysis and you find out that you only achieve a power of 0.68? Well, you just report it, and just be transparent to the reader in reporting your statistical results. It shouldn't happen that way, though. All right, gang, pretty sure that's all I got. Yeah. I hope this helped bridge the gap a little bit between the last stats class that you had and the beginning of some pretty cool stuff in 6610 and 6620. Take care.